So thank you, Mike, for this new episode on my YouTube channel, Scuola di Filosofia di Fornace. Last time, we discussed the importance of water, See the Wonder of Water, 2017. Today, we'll discuss the amazing world of the cell, and as we will see, water has a certain role even in this field. We're going to take the subject matter of today's interview from your book, The Miracle of the Cell, 2020, Discovery Institute Press. I strongly recommend everyone who has an interest in the field of biology and biochemistry to read this book in order to understand why the cell is amazing, quoting the title of the first chapter of the book. Trillions of cells do compose our physical body and are constantly replaced through a marvelous mechanism. In your book, Mike, you discuss the peculiarities of the cell. Of course, it won't be possible to present them all in our discussion. We'll try to concentrate on some particularly fascinating points. So, let's begin with the first question. First question. Since it is always important to define the object of this discussion, how would you define the cell from a purely scientific point of view, Mike?
Well, the cell is a minuscule particle of matter, which carries out a vast number, it contains within it a vast number of molecular machines, which are exquisitely designed to carry out a host of biochemical and catalytic functions. Not only does it carry out in the cell a vast number of different biochemical functions, it also replicates itself. The entire complement of macromolecules and functional entities in the cell is replicated. So that's and it's a tiny particle of matter, which is invisible to the human eye, of course, and it's surrounded by, in fact, basically a special membrane, which is a bilipid membrane around the cell. So that's what it is materially. It's an invisible speck of matter, which contains a huge number of exquisitely designed molecular machines, which carry out a whole series of different functions, and so forth. So that's what I would sort of, first of all, describe the cell as. Yeah.
Okay, thank you. So, Mike, let's come to our second question. In The Miracle of the Cell, you indicate the cell as a compressed complexity. And quoting you, every decade of research has revealed further depths of complexity. Fascinating is where you define the cell as a third infinity, and always quoting your book, where the cosmos feels infinitely large and the atomic realm infinitely small, the cell feels infinitely complex. Could you talk about the compressed complexity?
Yep, be delighted to. I recently wrote a small article about this, which I think an appropriate answer to, to your question is to read it.
Thank you.
So here we go. Although tiny and quite invisible to the naked eye, 50 typical body cells could sit side by side on the head of a pin. The complexity compacted into these tiny particles of matter is way beyond ordinary human comprehension. Many typical body cells contain some 10,000 million proteins, the basic working components of the cell. A figure nearly twice the total number of humans on Earth. Moreover, each of the 10,000 million protein machines is itself a wonder of atomic architecture, composed of several thousand atoms arranged in a highly specific configuration, carrying out either individually or in complex multi-protein assemblies of up to 10 proteins, particular chemical reactions, serving all sorts of diverse metabolic and structural ends. And we also know that some of these chemical reactions are carried out at speeds which are also beyond ordinary comprehension. One protein, the enzyme catalase, catalyzes the conversion of 2 million peroxide molecules to water and oxygen every second. And another enzyme, carbonic anhydrase, upon which our ability to excrete carbon dioxide in the lungs depends, converts 600,000 bicarbonate ions to the gas carbon dioxide every second. The enhancement of the speed of chemical reactions by some enzymes is also quite beyond our ordinary experience. In one case, increasing the speed of reaction 10 to the 21 times. Again, when certain ion channels open in the cell membrane of nerve cells, the rate of movement of ions through the gate is up to 100 million every second. In short, science has revealed that the carbon-based cell represents a realm of sophisticated molecular engineering transcending anything dreamt up by even the most ambitious nanotechnologists of today. A level of complexity vastly greater than anything in the mundane realm of our everyday experience, the complexity of a jumbo jet and much more packed into a particle less than a millionth of the volume of a typical grain of rice. And most likely there is far more complexity still to uncover. As Erica Hayden confessed in a recent Nature article, as sequencing and other new technologies spew forth data, the complexity of the cell has seemed to grow by orders of magnitude. And unlike any jumbo jet, or indeed, unlike any complex machine built or conceived by man, including the most ultra conceptions of 21st century nanotechnology, this wondrous particle of matter can replicate itself. From everything we now know, the cell would seem to represent the ultimate expression in material form of compacted adaptive complexity. Simply stated, cells are by far the most complex particles of matter in the observable universe, and it is hardly conceivable that anything more complex could be compacted into such a small volume. So that's what I read recently, but I think that sums up compacted complexity. These things are simply miracles of complexity compacted into an invisible speck of matter, the most complex speck of matter in the universe. Yeah,
it's like having a universe into an atom.
Exactly. Yeah. And there's, I don't know, there's about 10 to the 14 of these extraordinary objects making up the human body. Yeah.
And it is really a working universe, a universe which works, which that's fantastic.
Works.
That's great. Yes. Yes.
And it makes itself and remakes itself. Yes.
So, third question. Many times in our past discussions, we talked about carbon-based life. Now, you describe the importance of carbon for the cell, writing about its multiple fitness. Would you expose some properties regarding the role of carbon within the cell and for cellular life itself?
Yes. Okay. Well, one of the properties of carbon, which makes it a vastly important compound, is the fact that unlike any other atom in the periodic table, carbon bonds with itself in forming stable chemical bonds. And this means that, in fact, carbon can form long strings of molecules, string-like molecules like you get in fatty acids and fats, and it can form rings of molecules like you get in sugar and things like that. So the ability of carbon to unite with itself, forming limitless complex systems of either strings or rings, that's the key property of carbon, which leads to the vast emporium of carbon compounds, organic compounds. And in fact, nearly all organic compounds contain at least two carbon atoms bonded together. Amino acids contain two, sugars contain 5, and nitrogenous bases contain 3. And not only that, all the other atoms which form the carbon universe, hydrogen, oxygen, and nitrogen, they're bonded together in the inorganic molecules via carbon. In other words, nitrogen is linked to something else via a carbon and so forth. So carbon is the glue which glues all the other atoms together in organic compounds. And so basically it provides, what is an emporium of vastly diverse compounds. Some of them are gases like methane. Some of them are, there's like lactic acid. Some of them are waxes. There's a vast diversity of organic compounds. And that's what you need for the cell, because if you look at the metabolic charts on biochemistry departments, you'll find there's hundreds of different metabolites in the cell. And we now know from recent studies that the total number of metabolites in, for instance, trees or in life on Earth is in the order of millions. So if you're going to build a biosphere like that on the Earth, you need millions of metabolites. You need millions of different compounds. And even in our own cells, there's thousands of different metabolites. So that's what you is the carbon atom, because primarily it's the only atom which can bond stably with itself, forming long strings, rings, and all sorts of complex configurations. That's the key thing. Carbon also is able to make 4 chemical bonds with other atoms. It bonds with nearly all the other atoms in the periodic table, and particularly forms stable, strong bonds with oxygen, nitrogen, and hydrogen, which are the other 3 atoms which make up biomatter with carbon. So that's the most important thing, I think, that it forms stable compounds with itself. That's the key, which does it, yeah. So that I think is the thing which we should focus on. Yeah.
Thank you. And after carbon-based life, we are going to come to the DNA. A part of your book is also focused on this macromolecule. You affirm that the discovery of the structure of the DNA, double helix, was one of the seminal discoveries of the 20th century science. Anyway, you write, it is possible to conceive of carbon-based life without DNA, one that uses another self-replicating genetic polymer. What is unarguable, however, is that the functions of all the macromolecules in current biological systems on Earth depend critically on the ability to deploy multiple atoms, sometimes thousands, in a very specific irregular spatial conformations. No chemical life that we can conceive of would be feasible without complex molecular machines that can carry out definite tasks. I quoted you. Could you explain the content of this quotation, please?
Yes, basically, okay, let's go back a little bit into the history of biology in the 20th century. Before the molecular biological revolution, which revealed the nature of proteins, the structure of DNA, and so forth, the properties of enzymes, enzyme catalysis, for instance, was considered quite mysterious. Nobody could really explain how it occurred. And of course, the transmission of genetic information was completely mysterious. Nobody had the faintest idea how it could be done. And there was a widespread, what you might call, vitalist tendency in biology in the first part of the 20th century, because biologists said, look, you're never going to be able to explain this in terms of the laws of chemistry and physics. Well, from 1940 to 1960 occurred one of the great revolutions in scientific history, the molecular biological revolution. And at the core of that revolution was the realization that you can build molecules with very complex shapes, macromolecules with complex shapes, and these shapes can be complementary with other shapes. And that is the sort of, in a sense, the secret of life, that you can actually build very complex molecules. So you can get a substrate which can fit into an enzyme, and you can get 2 strands of DNA which can fit together. Okay, and so basically the realization that you can build great macromolecules with very specific architectures to carry out these specific functions, like the genetic function or like the enzyme, the catalytic function of an enzyme, dispensed with the old vitalist idea, because now it was possible to explain in terms of complex architectures with the laws of chemistry and physics, plus the realization that you can build these complex architectures. You can explain enzyme catalysis, and you can explain genetic transmission of information. So the old vitalism went, and as Jim Watson explains in his Molecular Biology of the Gene, in chapter 2, he calls it cells obey the laws of chemistry. Now, in 1940, some people would disagreed with that. But by 1960, everybody would be agreeing that cells obey the laws of chemistry. We'll come to this point later when we talk about the origin of life, because, and I'm preempting what I'm probably going to say. So although life, the cell was reduced, the functions of the cell as it exists today, although that was explained in terms of the laws of chemistry and physics, the great omission was that this same revelation didn't explain how the first cells arose, how the information arose to make a protein and so forth, how the whole integrated system came about. But it was a major reduction of life, as it were, to chemistry in one sense. But it didn't solve the second problem. How did this stuff arise? And of course, even today, nobody solved it. Sorry, I'm preempting what we might talk about later. But it fascinates me that great reduction didn't answer that second question. How did this stuff arise? How did these amazing particles of matter come about? Yeah.
Thank you. So our fifth question. In the third chapter of your book, Carbon's Collaborators, you talked about the electronegativities of hydrogen, carbon, oxygen, and nitrogen, which worked together amazingly towards the formation of the cell membrane and the folding of proteins. Then you present a list of properties for the fitness of the cell membrane: semi-permeability, self-organization, membrane diversity, right white membrane potential, and so on. Already discussing semi-permeability, you admit that for the survival of the cell, this mechanism had to be fully ready from the beginning. So my question is if it can be an example of irreducible complexity.
Okay, yes. Well, basically, the first thing to say is, yes, I think the cell is an example of irreducible complexity, because the life of the cell depends on a whole lot of integrated systems, mitochondria making energy, the DNA containing genetic information, the ribosome, the translational system, and everything else. And all this has to be there together to give you the life of the cell, for a functioning cell. But to come back to the formation of the membrane, this for me is one of the things that really, really amazes me of everything else, right? If you ask, well, how do we get cell membranes? Well, first of all, basically, we get them because of the differing electronegativities. This is a bit technical, I must say, but the different electronegativities of hydrogen, carbon, nitrogen, oxygen. Perhaps you can see this. I don't know whether you can see it. Anyway, basically, it turns out that, in fact, hydrogen and carbon, their electronegativities are close. And that means that in compounds containing CH bonds, neither the carbon or the hydrogen gets charged. It doesn't attract electrons compared with the other atom. So they're both sort of equally attract electrons, and neither part of the molecules containing CH bonds are charged, right? So they're not uncharged. They're called non-polar. But it turns out that, in fact, basically, if you take oxygen and hydrogen, there's a huge difference in electronegativities. And this means that, in fact, the oxygen draws the electrons from the hydrogen, and water, which is H2O, is a highly polar molecule with one part negatively charged, one part positively charged. And being a polar molecule, it doesn't like hydrophobes, like the hydrocarbons, which are uncharged, and it excludes them from the aqueous phase. And so that's why in phospholipids, the lipid bit is excluded from the aqueous phase because of the hydrophobic force of water. Water's dislike of these uncharged entities. Get out. kicks them out of the aqueous phase. And so you get the bilayer, the lipid bilayer membrane, okay? So that arises from the electronegativity of these atoms. But this is the amazing thing, which forces on you some design hypothesis, because it's amazing. Because what happens then is it generates the membrane, but the membrane, and it's the one characteristic which amazes, it's self-forming, self-repairing. So it surrounds the cell there's no need to have a complex repair system or anything like that. It just does it automatically. So it surrounds the cell automatically and repairs itself and looks after itself. And it has electrical properties. Without those electrical properties, there'd be no nervous system. There'd be no higher order nervous systems depending on electrical transmissions and so forth. And then it's semi-permeable. On the whole, it lets, as it were, small non-polar compounds in quite easily. It also lets some polar compounds, like small ones like water, through actually the membrane. It's semi-permeable, but it keeps inside the cell all the charged molecules, organic acids, amino acids, and then big things like proteins. So it holds everything inside the cell. It's semi-permeable to small molecules, and basically it's self-forming. And that's, and then it's got electrical properties. So all those properties are emergent in the membrane. So there's one level of self-organization which generates the electronegativities and the polar and non-polar compounds, and then inevitably another level of self-organization gives you the cell with its remarkable properties. That's one of the most amazing stories in biology, that actually. And if you want fitness of nature for the carbon-based cell, this is a wonderful example, and it's also a marvelous example of design. It's like there's a hierarchy here of design, which is absolutely beautiful. It's beautiful, yeah. So,
thank you. No,
I hope I'm not being too effusive. Yeah,
it's really a miracle, really.
It's a miracle. You talk about the miracle of the cell. This is one of the miracles of the cell. Yeah.
So, question number 6. We come to water. Water again.
Water again, yes, okay.
Yes, the role of water in chapter 7 of your book, which is called The Matrix, as the universal solvent becomes clear. And you talk about the temperature range from -20 degrees to 122 degrees, in which water is liquid, explaining then that this is only a tiny fraction of the total range of all temperatures in the cosmos, with respect to the super hot conditions in the Big Bang and the absolute zero. You define the existence of the cell and liquid water within this range as a miracle. What do you mean? Yeah. I think it's clear, but again, it's something marvelous.
Well, basically, the temperature range for organic chemistry is almost exactly the same range as the temperature that water is a liquid in the ambient conditions on Earth. Of course, water can be a liquid at higher temperatures if the pressure is greater, like in the hydrothermal vents in the ocean or in the deep crust. Water there can exist at higher temperatures. But we now can say, I think from experimental evidence, that carbon-based life can exist from -20 centigrade to 120 centigrade. And water, of course, is a liquid on Earth in that temperature range. But as you say, the miracle is if that correspondence didn't occur, there'd be no carbon-based life in the universe, because water is the ideal matrix. It has the hydrophobic force. It's a wonderful solvent. It's got a low viscosity, so things can diffuse through it. And so, it's the ideal perfect matrix for the cell, but it has to be a liquid in that temperature range between sort of close to 0 and 100. So where you can carry out all the organic biochemical reactions you want in that temperature range, and water is a liquid to allow you to do it inside it. So that's amazing. And as you say, the temperature of the Big Bang was 10 to the 30, I think, something like 10 to the 30 centigrade. The sun's temperature is 15 million centigrade. Some supernovae explode, and the temperature, I think, is, I'm reading from my notes, is 10 billion
Yeah.
centigrade. So there's a vast range of temperatures in the cosmos, from absolute zero, which is minus 270 roughly centigrade, right away up to the temperatures of the Big Bang. And in this vast range of temperatures, water, the matrix of life, is a liquid in just the temperature range you need to carry out the reactions of organic chemistry. So, it's another miracle.
Yeah.
So there's the miracle of the cell, there's membrane, and there's the miracle of the temperature range. Yeah. Yeah.
And then, Mike, you quote supernova, Big Bang, and I quote the field of astrobiology, because you talk also about astrobiology in your book. In 1969, there was the fall to the Earth of the Murchison meteorite, whose chemical analysis showed the presence of some organic building blocks of life. These and such other facts as the synthesis of the chemical elements in the stars reveal, quoting you, that the cosmos is seeded with a vast inventory of organic chemicals, including amino acids and nucleobases, the starting points in the assembly of the two main polymers, proteins and nucleic acids, in carbon-based organisms. The analysis of the interstellar gas does also reveal that the cosmos is seeded, always quoting you, not just with some of the basic monomers of life, but also with far more complex carbon compounds. So, you explain that carbon-based life as it exists on Earth is no artifactual accident, but an inherent part of the natural order, an internal part. It is an inherent part of nature's grand design from the moment of creation. However, as you write, we don't know how and where the transition from pure chemical elements to the cell did occur. And this is among the greatest unsolved problems in science. You write, we know life has graced our planet for billions of years, but we know virtually nothing about how it originated, as you said before, for example. Can you comment that, please?
Yeah, well, as I say, I've already made one comment that, in fact, during the mid 20th century revolution in biology, the functioning of the cell was essentially reduced to chemistry. I think that would be agreed by nearly everybody. But of course, the actual fundamental design of the cell, how the cell came about in real time, is completely mysterious, and nobody knows. All I would say is, from the evidence of fitness that I see, you can say that however the cell came about, it was by design, because there was as it were, the fitness is essentially a primal blueprint, a specification for the cell in the nature of things from the beginning. So therefore, however it occurred, it's clearly by design. Most of my life, I've sort of tended to think there'll be some natural explanation for this. We'll find out that the steps from chemistry to the cell, there's some natural explanation for it, some chemical explanation for it, just like there was a chemical explanation for the functioning of the cell in the mid 20th century. But I don't know. At the moment, this looks totally intractable, and I don't see any real advance in my whole lifetime. I've seen no advance at all towards solving this problem in terms of known laws of chemistry and physics. So, I mean, how it came about is a total mystery, except we can say from fitness that it's there by design. And you can put it like this: if it turned out that the origin of the first cells required a miracle. That's by design, obviously. But even if it does occur in some natural way, it's also by design. So the fitness constrains all theorizing about the origin of life. And it theorizes around one fundamental claim. Life is here by design, by the fitness of certainly the four atoms which make up most of biomatter and the periodic table of elements. Life is here by design. Exactly what the steps were in real time to actualize the cell, we don't know. And it's an open question whether it was something like special creation or it's some naturalistic explanation in terms of chemistry and physics. So that's where we're at. And for me, it's intellectually very satisfying to know from the evidence of fitness that as you said earlier as you're reading from, I think, the book, or it's your own words, basically nature was prefigured for this from the beginning. And so, however the actual things occurred in real time, the prefiguring was there. The designer had already organized matter for the carbon-based cell from the beginning.
Yes, and in this sense, all biology and its laws are a miracle. In this sense,
yes, yes. In that sense, it's a miracle already. Yeah, it's a miracle. Just how exactly that miracle was actualized in real time, we don't know. But there's a lot of people who would lean towards special creation and so forth. So, but we don't really know how it happened. We have to find out.
Thank you.
Perhaps this century we'll find out. I'm sure I won't be here. I won't be here to observe it, but yeah, there'll be a lot more light shed on this over the next decades of research. Yeah.
So last question is always the hardest question. So in chapter 8,
okay, what's
no,
I know what's coming. I think.
Yeah,
I did read your.
Okay. So I read it for our guests and so on. In chapter 8, you give a list of 9 peculiarities forming the primal blueprint, which was indispensable for the emergence of the carbon-based cell. This all, quoting your book, poses a challenge to the Darwinian worldview. However, the first cell was assembled, whether suddenly through the direct agency of a diving watchmaker or gradually by a blind Darwinian watchmaker. Its creation was only possible because the blueprint was already in place. You conclude that all information you discussed in the miracle of the cell provides more convincing evidence of design in and nature and purpose in the universe than the fine-tuning of these atoms for the carbon-based cell. The evidence presented in this monograph conveys the irresistible impression that the properties of the atoms have been contrived directly and purposefully to enable the existence of life in the universe. This is also a reduction of Darwinism, as you conclude. I would like you to ask for a final comment on this point. The reduction of
Darwinism.
Yes,
I mean, basically what it would mean is even if we assume that life arose by some form of, by the way, I don't believe this, but even if we assume it arrived by some sort of Darwinian process, Darwinism is still insufficient, because if it wasn't for that fitness which existed in nature from the beginning, Darwinism couldn't create a cell. I mean, I'm not saying that Darwinism did create a cell. I'm pretty sure it didn't. But nonetheless, if you want to be a hard-headed sort of agnostic and say, well, Darwinism created the first cell, okay. But Darwinism only created the first cell because of the constraints of the laws of nature and the fitness of nature for the cell, which was there from the very beginning of time, from the moment of creation itself. So in that sense, basically, it greatly undermines the philosophical significance of any Darwinian claim. You can't say that Darwinian natural selection created the cell. That's simply not true. If Darwinism was involved in any way, it was channeled by design from the beginning, from the moment of creation itself.
Thank you, Mike. Thank you, thank you. There are several properties and functions of the cell we didn't analyze because there wasn't time in this interview. However, everyone can find them in the book, The Miracle of the Cell. In the next episode, Mike will talk about light with Mike's Children of Light. So again, thank you, Mike, for our discussion, and see you next time.
Probably see you next year now.
Yeah, next year.
Okay.
Next year.
It'll have to be next year now, yeah. Yeah.